In this course module, we will cover the fundamentals of threat intelligence, modeling, and sharing. In particular, we present an overview of TI, maturity models of TI, the MITRE attack framework, the cyber kill chain, threat actors, and courses of actions as they pertain to the cyber kill chain, and threat sharing. Upon completion of this module, students should be able to assess threats to and vulnerabilities of computer systems to develop a secure risk profile, identify threat tactics and methodologies, monitor and report on validated threat activities, determine tactics, techniques, and procedures, TTPs, for intrusion sets, and share threat intelligence in various formats. We start with the fundamentals of threat intelligence and threat modeling. So, what is threat intelligence? Threat intelligence involves the analysis of adversary capabilities, motivations, and goals. When used in cyberspace, it is referred to as cyber threat intelligence, CTI. It starts with collecting data. Essentially, it is the process of and the analysis of data to arrive at actionable information. Models are used to effectively act on and generate intelligence. Two models that will be discussed are the Observe, Orient, Decide, Act, OODA loop, and the Intelligence Cycle model. In the Observe, Orient, Decide, Act loop, Observe stands for data gathering from both internal and external sources. Orient is putting that data in context, correlating with other data and information. Decide entails brainstorming various actions, their capabilities, feasibilities, consequences, and costs. And Act is a follow-through with the chosen course of action. Here are the stages of the intelligence cycle model. The direction stage consists of the following: what question will the intelligence answer, and what is the primary goal? In the collection stage, data collection is made to answer those questions. In processing, data processing activities such as normalization, indexing, sorting, filtering, prioritizing, and others are done. In the analysis stage, most systems use humans as primary analysis drivers. The goal is to answer the questions. In dissemination, the results of the data analysis are shared. And in the feedback stage, communication with top management and other stakeholders are made to gather the necessary decisions on the course of actions. The Cyber Threat Intelligence Capability Maturity Model is a hierarchy of processes that consist of 5 levels. Level 0, also called initial, is purely ad hoc process and is unpredictable. Level 1, or repeatable, is a reactive, volatile, and manual process. Level 2, or defined, is a documented, standardized, and reviewable process. Level 3, or managed, is a proactive, metrics-driven, and with some automation. Level 4, also called the optimization level, is automated, integrated, and predictable. The MITRE attack is a globally accessible knowledge base of adversary tactics and techniques based on real-world observations. The attack knowledge base is used as a foundation for the development of specific threat models and methodologies in the private sector and government and in the cybersecurity product and service community. This slide depicts the MITRE attack framework. MITRE developed the attack framework as a more technically detailed characterization of cyber attacks. ATTACK stands for Adversarial Tactics, Techniques, and Common Knowledge. There are three high-level frameworks: Enterprise, Mobile, and ICS. The stages of cyber attacks are very similar to the kill chain, but ATTACK breaks some stages into multiple options and gets into specifics about how to perform a stage. A TTP defines how an adversary might go about accomplishing a cyber attack stage. A tactic is the highest level description of this behavior. Techniques give a more detailed description of behavior in the context of a tactic. Procedures are an even lower level, highly detailed description in the context of a technique. Beneath each stage in the framework is a list of techniques an adversary might use to accomplish this stage. Each technique is hyperlinked to a detailed page explaining that technique. Techniques have IDs and often associated sub-techniques. The term kill chain is a military concept related to the structure of an attack, consisting of target identification, force dispatch to target, decision and order to attack the target, and finally, the destruction of the target. Developed by Lockheed Martin, the cyber kill chain framework identifies what the adversaries must complete in order to achieve their objective. The Lockheed Martin cyber kill chain consists of 7 mission stages. Number 1, reconnaissance. Number 2, weaponization. Number 3, delivery. Number 4, exploitation. Number 5, installation. Number 6, command and control, C2. And number 7, actions on objectives. Understanding who the threat actors are and the methods of attack is critical to effective cyber defense. This is categorized using a military term as tactics, techniques, and procedures, or TTPs. Tactics refer to the art or skill in achieving a goal. Techniques are the methods that are employed that are often unique to the attacker, i.e. specific signatures that might identify the writer of malware. The procedures are the actions that are taken during an attack. Port scans, for example. This table depicts the different types of threat actors with varying levels of sophistication and expertise. A course of action, COA, matrix is a table that shows the defensive capabilities available at each phase of the cyber kill chain. These defensive capabilities are the following: discover or identify the adversary's past activity, i.e. logs, detect or identify adversary's current activity, deny or prevent adversary activities, disrupt or interrupt adversary's activities or flow of information, degrade or reduce effectiveness or efficiency of adversary's activities or flow of information, deceive or mislead the adversary, and destroy or damage the adversary's infrastructure so it will not function. This slide depicts an application of the courses of action matrix as illustrated in a paper published by Hutchinson et al. At Lockheed Martin. For example, during the reconnaissance phase, a firewall ACL will deny the successful execution of that kill chain stage. Another example is the use of an inline antivirus to stop the successful execution of the delivery stage of the kill chain. We now turn our attention to threats in an ICS environment. Here are ICS protocols and security considerations. Timeliness and performance requirements. ICS are generally time-critical with a criterion for acceptable levels of delay and jitter dictated by the individual installation. Availability requirements. Many ICS processes are continuous in nature. Unexpected outages of the system that control industrial processes are not acceptable. Outages often must be planned and scheduled days or weeks in advance. Exhaustive pre-deployment testing is essential to ensure high availability, i.e. reliability, for the ICS. Risk management requirements. In a typical IT system, data confidentiality and integrity are typically the primary concerns. For an ICS, human safety and fault tolerance to prevent loss of life or endangerment of public health or confidence, regulatory compliance, loss of equipment, loss of intellectual property, or loss or damaged products are the primary concerns. System operation. ICS operating systems, OS, and control networks are often quite different from IT counterparts, requiring different skill sets, expertise, and levels of expertise. Control networks are typically managed by control engineers, not IT personnel. Additional ICS protocols and security considerations. Communications. Communication protocols and media used by ICS environments for field device control and intra-processor communication are typically different from most IT environments and may be proprietary. Change management. Change management is paramount to maintaining the integrity of both IT and control systems. Unpatched software represents one of the greatest vulnerabilities to a system. Software updates on IT systems, including security patches, are typically applied in a timely fashion based on appropriate security policies and procedures. Managed support. Typical IT systems allow for diversified support styles, perhaps supporting disparate but interconnected technological architectures. For ICS, service support is sometimes via a single vendor, which may not have a diversified and interoperable support solution from another vendor. Component lifetime. Typical IT components have a lifetime on the order of 3 to 5 years, with brevity due to the quick evolution of technology. For ICS, where technology has been developed in many cases for very special uses and implementations, the lifetime of the deployed technology is often in the order of 10 to 15 years and sometimes longer. Component location. Most IT components and some ICS are located in business and commercial facilities physically accessible by local transport. Remote locations may be utilized for backup facilities. Distributed ICS components may be isolated remote and require extensive transportation effort to reach. This list of vulnerabilities on ICS is not exhaustive. We represent herein some of the most important. Inadequate change and configuration management. Mostly, configuration changes and patches are not verified for correctness. Inadequate continuity of operations or disaster recovery plan. In this case, emergency response procedures unintentionally omit security controls. Inadequate network segmentation. An example is the OT network is connected to untrusted networks or that network interfaces permit unnecessary traffic flows. Insufficiently trained personnel. Workers are not trained on security policies and procedures. Physical access to devices. Physical devices such as PLCs, sensors, switches, and others are not properly secured. Weak authorization and authentication mechanisms on control. This vulnerability on weak authentication processes or authorization keys is prevalent on legacy systems. Use of insecure protocols such as Modbus and DNP3. Unfortunately, many ICS and RE systems are operating with these insecure communication protocols. Attacks on industrial control systems may include one or more of the following. IT/OT insider. A disgruntled IT or OT operator or technician can easily snoop for a privileged password to carry out a malicious attack on ICS RE systems. Ransomware. An inadvertent virus upload or an email phishing can trigger a ransomware attack similar to what happened in the Colonial Pipeline attack. Ukrainian energy attack was perpetrated through phishing by a nation state and shut off power to over 200,000 people for up to 8 hours. Market manipulation. Organized crime syndicates target vulnerabilities in IT systems to get to the OT systems and manipulate the control equipment to react during high energy or commodity demand. This will, in turn, control the supply of that commodity and manipulate the market. Mobile phone Wi-Fi. The attackers would plant malicious software on mobile phone apps and continuously scan for Wi-Fi networks in critical infrastructure workplaces. The Wi-Fi network, if left unprotected, can be compromised at that workplace. Additional attacks are the following. Hijacked two-factor. The sophisticated attacker compromises the two-factor authentication mechanism to attack the remote access of the critical infrastructure from the home network of the operator. Industrial Internet of Things pivot. Poorly defended industrial IoT devices are used as entry points for attack in this case. Malicious outsourcing. The outsourcing of remote support functions for control system components may be used to compromise an ICS RE system. Compromised vendor. The poorly defended vendor website may be compromised and could serve tainted patches for control system devices. Compromised remote site. A remote site that is not physically secured could be the source of malicious software that might propagate into the main network. Here are some mitigation techniques to ICS threats and attacks. IT/OT Insider. Use network segmentation and failsafe controls. Ransomware. Use removable media control and a unidirectional gateway. Ukrainian Energy. Use multi-factor authentication and email filters. Market manipulation. Use continuous monitoring and input validation. Mobile phone Wi-Fi. Use intrusion detection systems and secure the Wi-Fi networks. Additional mitigation techniques are the following. Hijacked two-factor. Use unidirectional gateway and disallow remote control. Industrial IoT pivot. Strengthen IoT security and use segmented networks. Malicious outsourcing. Disallow remote control and carefully vet outsourcing vendors. Compromised vendor. Require periodic check of vendor site and virus scanner. Compromised remote site. Physically secure the remote site and ensure access control. The increased security risks brought about by renewable energy opens new trends to cyber threats. These trends are the following: the increased connectivity and insecure connections, the adoption of standardized technology with known vulnerabilities, the increase in IT/OT connectivity, the increased availability of technical information which enables hackers to better understand the RE system architecture, the increased reliance on automation, and the introduction and integration of new energy sources. We close this module by examining threat sharing. Reasons for threat information sharing include the following. 1. To leverage collective knowledge to fight threats. 2. To gain a better understanding of the threat landscape. 3. To be able to make well-informed decisions on detection and mitigation. And 4. To improve threat-related controls, processes, practices, and tools. Types of threat intelligence are the following. Indicators of compromise. These are digital artifacts such as log files or entries, network packets, etc., that indicate attacks or threats on a system or network. TTPs. These are nuggets of information from the knowledge base of the MITRE ATT&CK framework. Security alerts may come from intrusion detection or prevention systems. Threat intelligence reports that are produced by reputable entities on the internet such as SANS, Cisco, Palo Alto, CrowdStrike, or Dragus. And tool configurations or settings. These are threat informations produced by customized threat collection tools. Threat intelligence sharing standards include the following. OpenIOC is an open framework meant for sharing threat intelligence information in a machine-readable format. It was developed by Mandiant in 2010. The Incident Object Description Exchange Format, IODEF, defines a data representation that provides a framework for sharing information commonly exchanged by computer security incident response teams about computer security incidents. The traffic light protocol is a system for classifying sensitive information created in the early 2000s by the UK government's National Infrastructure Security Coordination Centre to encourage greater sharing of sensitive information. Open Threat Exchange, OTX, is a threat data platform that allows security researchers and threat data producers to share research and investigate new threats. OTX provides open access for all, allowing you to collaborate with a worldwide community of threat researchers and security professionals. STIX, Structured Threat Information Expression, is a standardized XML programming language for conveying data about cybersecurity threats in a common language that can be easily understood by humans and security technologies. Trusted, automated exchange of intelligence information defines how cyber threat information can be shared via services and message exchanges. It is designed specifically to support STIX information, which it does by defining an API that aligns with common sharing models. CyBox is a standardized language for representing cyber observables, whether dynamic events or stateful properties that are observable in the operational cyber domain. The Collective Intelligence Framework is a cyber threat intelligence management system. It allows you to combine known malicious threat information from many sources and use that information for identification, detection, and mitigation. MISP Threat Sharing is an open source threat intelligence platform. The project develops utilities and documentation for more effective threat intelligence by sharing indicators of compromise. In STIX, domain objects representing concepts in the cyber domain and used to describe things are related to each other using STIX relationship objects, SROs. Complex representations of cyber threat intelligence can be expressed by connecting multiple SROs. This slide depicts the STIX objects. Each of these objects has certain attributes that fully define itself. Notably, missing in this diagram are the lines connecting the objects with each other, indicating their relationships with each other. This slide displays a network traffic object with attributes such as IPv4 addresses, protocol types, etc. A trusted automated exchange of intelligence information, or TAXI, defines a RESTful API offering two primary services, collections and channels to support threat intelligence sharing models. TAXI services include the following: inbox service, used by a TAXI client to push information to a TAXI server. Poll service, used by a TAXI client to request information from a TAXI server. Collection management service, used by a TAXI client to request information about available data collections or request a subscription. Discovery server, used by a TAXI client to discover available TAXI services. MISP is an open source threat intelligence sharing platform that can be freely downloaded as an independent server or an instance. MISP offers the following features. It provides an efficient IOC and indicators database. It provides an automatic correlation of indicators with attributes. It has a built-in sharing functionality. It offers an intuitive user interface. It enables the export of threat information to multiple formats: JSON, CSV, OpenIOC, text, etc. It provides a flexible API for customization and integration, and it affords STIX support. The categories of threat intelligence are strategic, operational, and tactical. The strategic type places threat in business context and describes strategic impact informing risk management and organizational direction. The operational type is focused on adversary behavior, holistic remediation, threat hunting, purchasing decisions, and data collection. The tactical type is focused on technical indicators and behaviors to inform network-level action and remediation. Now, let's look closely at strategic intelligence. The primary audience of this type of intelligence are security and organizational leadership personnel. It is the who and why of threat intelligence. So, who is behind the threat, and what are their motivations? What makes the organization a vulnerable target, and what can the organization do to reduce the risk? Next, we look at operational intelligence. The primary audience of this type of intelligence are threat hunters, security leadership, and incident responders. This is the how and the where of threat intelligence. It includes incident analysis, attack pattern and attribution analysis, malware analysis, and scope analysis. Next, we look at tactical intelligence. The primary audience of this type of intelligence are security operations analysts, network defenders, and incident responders. This is the what of threat intelligence and involves the lowest level of information, such as IOCs and other observables that can provide insights to adversary TTPs. Now we look at the tools and techniques for each of the TI categories. On strategic intelligence, the tools and techniques include periodic briefing, daily or weekly, threat sharing agreements, IR or threat hunting plans, security policies, and system prioritization. On operational intelligence, the tools and techniques include a knowledge of adversary tools and techniques, a knowledge of vulnerabilities, and currently known mitigation techniques for known threats. On tactical intelligence, the tools and techniques include adversary TTPs, a knowledge of attack vectors, knowledge of IOCs, systems affected, and other observables to better understand the threat.